Hello everyone, welcome back to Total Organic Chemistry. This video we're going to be taking a look at cyclohexane and what its properties are and what sets it apart from other cycloalkanes. So as we discussed in the previous video, big ring cycloalkanes, so larger than 3 carbons, they do not adopt a planar conformation. So we can maybe draw this hypothetical planar cyclohexane here where we have all 6 of these carbon atoms in the same plane. And then maybe we have I'll draw in a few of the hydrogens here. And we know that this conformation is not going to be stable at all because we have all of this eclipsing interactions between all of these hydrogens, right? And I've just drawn in a few, but also we have all of the hydrogens on the bottom as well. And remember, these are called our eclipsing or torsional strain. So there's going to be a lot of that if we have a planar molecules. However, so this is not going to be the case, right? And what we talked about in previous videos is that you can warp that molecule, that's what happens in real life, is that we have this 6-membered ring, cyclohexane, and it ends up adopting this sort of conformation here. And what we call this is the chair conformation, chair cyclohexane, and it accomplishes 2 things for us. First of all, if we draw in our hydrogens, and you'll get used to drawing these chair conformations as we practice more. If we draw in all of our hydrogens here, we notice that they alternate to where there are never 2 hydrogens on adjacent carbon atoms that are eclipsing. So we have alternating sort of up, down, up, down, up, down hydrogens. And so this gives us no eclipsing hydrogens, which is very good, very stable. And also the bond angles with this chair conformation end up being very close to the ideal tetrahedral bond angles. So not exactly ideal, but good enough to where this conformation is very, very stable, more so than smaller rings. And what we can do is we can draw a diagram similar to ones we've drawn before. Let's make it nice and big here on the page, where we have energy on the y-axis, and then we can have, let's say, the reaction coordinate of conformation change. So we can look at the different conformations of cyclohexane and see how those different conformations change in energy and how stable they are. So it's going to look something like this, where we have a minimum here, and that's going to be our chair. Let me give myself a little more room. So we have a minimum here. This will be our chair conformation. I'll draw it like that. And then if we twist one of the edges up, we're going to end at a maximum here, maximum energy, so very unstable. And this is going to be called the half chair, so let me see if I can draw it here. If we imagine moving this carbon up, then we get something like this. where we get 5 carbon atoms in the plane and 1 out of the plane. So you can imagine that's going to be very unstable. We have 5 sets of eclipsing hydrogens. So this is going to be our chair down here, half chair. And most of these conformations we're not going to really worry about, but the chair will be incredibly important for us. Then we'll get down to another minimum here, not quite as low as the chair itself, but this is going to be, here, let's come back to this actually. We're going to go up to another local maximum here in energy, and then it'll be symmetric over the next sort of cycle here. So this maximum here will be what we call the boat conformation. So thankfully these names are very intuitive, and this is our boat. So it looks like a little boat because both carbon atoms on the sides are pointed up on the same side instead of where the chair where they're pointed opposite from each other. And then we can draw this local maximum here is called the twist boat, which is a little bit trickier to draw. Maybe we can draw it like this. One, two, three, four, 5, 6. There's our twist boat. I will label that. So twist boat is slightly lower in energy, but not quite as low as the chair. And then we have the equivalent over here, just flipped. So half chair, twist boat, and then our other orientation of the chair, so we can imagine the chair flipping over to give us this chair on this side. So if you're having any trouble following this sort of diagram where we are looking at the potential energy versus the conformations or the angle between certain carbon atoms, feel free to subscribe to my channel and look at some of my previous videos that I've uploaded on these topics. It's always good to know. So why is this important in the first place? Well, like I said, cyclohexane imparts an extra stability to because of the lack of eclipsing interactions between adjacent hydrogen atoms. So what we can do is look at, if we draw our chair conformation again, so here's our chair, and you can draw the chair either way, with either this side pointing down or up. It does not matter. And if we take a look at our hydrogens, so when we draw chair cyclohexane, we're always going to have one hydrogen that is vertical, and this is called, so this is for each carbon, and this is called our axial hydrogen, and one hydrogen will be sort of slanted, horizontal, and this is what we call the equatorial hydrogens. And this is for each carbon. So I'm not going to draw them all in here, but actually let us do that. So, and then they alternate, so if we have one hydrogen going up here, the next axial hydrogen, so remember that's the one on the vertical axis, the next one will be going down. This one here will be going up. This will be going down. this will be going up and down. Oops. Down. So those two in the middle are kind of hard to draw, but those are our axial hydrogens. And same thing happens for equatorial. So we have an equatorial hydrogen here, and that's going to be slightly down and to the right. We can imagine that each of these carbons is adopting sort of a tetrahedral geometry. And this bond should be roughly parallel with this one. And then we'll have another hydrogen going up here. So this is our equatorial hydrogen. And see how, whereas this hydrogen is going down, so slanted and down, this one is slanted and up, and that will repeat. So we have slanted down, slanted up, slanted down, and slanted up. And see how each of these bonds to hydrogen is roughly parallel with the opposite. You can think of the opposite carbon-carbon bond. So this bond here is parallel to here. This bond to hydrogen is roughly parallel. Again, roughly. It's not a big deal if they're perfect or not. And then this bond to hydrogen will be roughly parallel with that carbon-carbon bond. And that goes for the equatorial hydrogens. And if I box the rest of these equatorial hydrogens in, equatorial, equatorial. Great, and we see that, remember, there are no eclipsing interactions because each of these hydrogens is alternating. So we have one going up here, one going down, one going up, one going down, one going up right in here, and then again this one going down. So there are no adjacent carbons with eclipsing hydrogens. If we flip this chair, so we can draw an equilibrium arrow and draw the flipped version, so the chair going the other way, which I am much worse at drawing. So I'm not going to be drawing all the hydrogens this time, but we can imagine now we have axial hydrogen. Remember, axial is up and down, and equatorial is slanted. And then on this side, equatorial, slanted, axial, straight up and down. And if I label, say if I label this hydrogen right here, let's pick this one on the side. This one is, so is this axial or equatorial? Well, it's slanted, not straight up and down. So this is going to be an equatorial hydrogen. And when we flip the chair, changes to axial. So when we flip the chair conformation, all of the equatorial hydrogens will change to axial. That's going to be this one. And vice versa. So all of the hydrogens that were originally in the axial position will now be in the equatorial position. And that's going to be important to keep track of as we move on. So how easy is this equilibrium here? Is one side favored over the other? Well, for cyclohexane with no substituents, we just have all hydrogens, this chair flipping is going to be incredibly fast at room temperature. So chair flips readily at room temperature. Just like rotation around single bonds occurs very quickly at room temperature for other alkanes. And so these chair flips will occur maybe tens of thousands, hundreds of thousands of times at room temperature, so we can't differentiate the two. However, if we add a substituent, that changes. So what if we take our chair cyclohexane, let me draw that a little bit better, and we add a methyl group. So if we add maybe a methyl group here, how does that change things? Well, now we have we still have our hydrogen in the axial position here, and that's pointing straight up. And then what if we draw the chair flipped version, where now we will draw the chair in the opposite orientation. And remember, we have our methyl group is equatorial in this position, so it's going to change now to the axial position. And now we have the hydrogen in the equatorial position, whereas it was in the axial position beforehand. So what does that mean? Well, if we take a look at the adjacent hydrogens, we have one hydrogen here, and one hydrogen here, and then we have maybe one hydrogen here, one hydrogen here, and then let's draw one more carbon over as well. Hydrogen and hydrogen. Go back to this one. We have one axial and equatorial. So why is that important? Why am I drawing in all these extra hydrogens? Well, only in one of these conformations do we have extra steric clashes. So what we have here is this methyl group will interfere with the hydrogen on the 3 carbon. So if we say that this is carbon 1, carbon 2, and carbon 3, then we have what we call a 1,3 diaxial interaction. So 1,3 because we have carbon 1 and carbon 3, substituents on those carbons, and it's diaxial because we have a methyl group axial and a hydrogen axial. So diaxial. And those interactions will be unfavored because we have our big methyl group bumping into that hydrogen and causing the energy of the system to increase. So that's going to be less stable overall. Whereas we have, for example, on this conformation, we do have 1,3 diaxial interactions between these two hydrogens, right? So 1, 2, 3 carbons, but those are both hydrogens. So hydrogens are small, they usually don't cause much steric hindrance, so it's not going to be as big of a deal. And our methyl group here is pointing out, so it's equatorial, it's pointing away from the ring, and it's not really going to experience any sort of steric hindrance or steric clashes with other substituents on the ring. So because of that, what we can do is we can alter our equilibrium arrow here, and we can say that the equilibrium will be only a little bit in that direction, and it will be mostly in the reverse direction to give us the equatorial substituent, to avoid those 1,3 diaxial interactions. So equatorial substituents are always favored. And in this case with methyl cyclohexane, so we have our methyl group and then cyclohexane, it's going to be about 95% of the equatorial and about 5% of the axial methyl group. So even just the addition of one methyl group will change that orientation from 50% of each to about a 95% ratio. What if we add more than one substituent? So for more than one substituent, we're going to take a look at whatever's bigger. Largest wants equatorial. So the 1,3 diaxial interactions are going to be more important for the very large substituents, and for that reason they are going to prefer the equatorial position. So before we take a look at different substituents, let's maybe do a dimethyl substituted cyclohexane, which is going to be something like this. So we have maybe one methyl group here, and remember this is equatorial because it's slanted, not straight up and down, so we can have maybe a hydrogen up here. If we draw that explicitly, it will be axial, and then maybe a hydrogen here and a methyl group equatorial on this carbon. And if we draw the ring flipped version, so the chair flipped conformation, then we have our methyl group here. Remember, equatorial changes to axial when you flip the chair, and equatorial again will flip to axial here. And then if we want to draw in our hydrogens, we can do that. They will also be flipped, so they were axial before, now they are equatorial. And which of these is more stable? Well, remember that we want equatorial substituents because they avoid the 1,3 diaxial interactions. So this one will be much more stable because both of those methyl substituents are in the equatorial position. More stable, both equatorial. Whereas this one, they're both axial. So that's going to cause a lot of problems, a lot of steric hindrance, and less stable overall. So one thing to think about is if we draw the bond line structure that we're more familiar with for this cyclohexane, this is going to have one methyl substituent going towards us and one going away. And so remember, the position of these in terms of whether those bonds are up or down or coming towards us or away from us is independent of whether they're axial or equatorial. So we can look at maybe this bond we say is going up, and this bond is going down. If you look at it the other way, just from maybe the other side, then it will be flipped, but in any case, these methyl groups are on opposite sides of the ring, and we can't change that. When we go through the chair flip, they will still be on opposite sides of the ring as they are over here. Now we have down and up. So this is what we call our trans substituted cyclohexane. Remember that trans substituted, trans is across. So trans is going to mean that those substituents are on the opposite side. And for trans substituted cyclohexanes, for example, for this dimethyl substituted cyclohexane, we have both substituents equatorial in this conformation and both substituents axial in this conformation. So that's rather easy for us to figure out which is more stable. But what if we have a cis substituted cyclohexane? Well, we can draw that here, where maybe we have our methyl here, and then now we have our methyl in the axial position this time. See how they're both pointing down, they're both on the same side of the ring. And if we do our chair flip, we will find out that it doesn't matter. So now we're going to have, remember, flip to axial from equatorial, and then flip to equatorial from axial. So these are equivalent because in both of our cases we have one axial methyl and one equatorial. So this is going to be a 50-50 split between those two conformations. Equilibrium will not favor one side or the other. And just for completeness, let's draw our skeletal structure again for this. And this is where we have one methyl group there coming towards us, and the other methyl group will also be coming towards us. So this is our Sis Substituted Cyclohexane. Remember, cis is the same side. So finally, for one last example, we've been working with the same substituents now, two methyl groups. What if we have two different substituents? So again, draw our chair, skeleton, and then what if we have a tert-butyl group, so where we have one carbon and then branched off of that are three methyl groups, so that is a very, very large group, and one methyl group here. So in this case we have methyl equatorial, and we have the tert-butyl group, or T-butyl group, you'll often see it abbreviated, axial. And we can draw the chair flipped version again, as always, where we flip, so axial to equatorial, and equatorial to axial. Now we have methyl axial, remember because they always flip, and our T-butyl group is now equatorial. So which of these will be more stable? Well, like I said just a minute ago, the larger group is always going to prefer the equatorial position. And that's because the larger group will experience more 1,3 diaxial interactions, or you can just think of it as more steric hindrance. And those steric clashes with the other hydrogens or other substituents, will contribute to decreased stability. So we want our T-butyl group to be equatorial in order to give us the most stable conformation. So this cyclohexane will prefer to be in this chair conformation instead of the other one, and if you measure the amounts, you probably see that it's a very large excess. So that concludes my video on cyclohexanes and substituted cyclohexanes. Again, thank you for watching, and please remember to like and subscribe, and check out my Patreon page, which will be linked in the description.